Welcome to part 3 of the lecture. I believe students in this class previously studied the linear regression with one independent variable, which is called simple linear regression, in an introductory statistics course. So let's go through a brief review of simple linear regression. Let's start with an example. Suppose we hypothesize that age-related physiological changes of blood vessels tend to raise blood pressure, because of age-related narrowing and hardening of blood vessels. Actually, this may be a well-established fact rather than a hypothesis. Anyway, the question is, in order to investigate the hypothesis, what would you do first if you have data on age and blood pressure? In such a case, a typical way to start data analysis is to plot systolic blood pressure against age, as shown in this figure. Here, the horizontal axis is age from 18 to 80, and the vertical axis is systolic blood pressure, ranging from 78 to 226. The points are scattered widely. The majority of the points appear to be in a broad band that goes upward diagonally from left to right, suggesting a tendency for systolic blood pressure to be higher at older adult ages. But it is a visual impression I had. Since the points are quite widely scattered, I am not very confident about my visual impression. Then the next step may be local averaging. In this figure, the red broken line was drawn by linking 7 points, each of which indicates the mean value of systolic blood pressure for a 10-year age group. The left end of the red line indicates that the average systolic blood pressure for those in the 20s is between 112 and 113, and then the average blood pressure tends to increase with age up to about 137 for the age group 70 to 80. The red line may appear quite flat, but it is mainly because the vertical axis ranges very widely from 78 to 226, because there are a few outliers whose blood pressure are above 200. Actually, the key concept of simple linear regression is that we fit a straight line to the points in a scatter plot. By doing so, we summarize the data, or identify a typical pattern in the data, using a simple mathematical form. This is a straight line that was fitted to the data points using linear regression. The straight line goes upward from left to right, suggesting that although the points around the straight line are scattered, the typical pattern is a rise of systolic blood pressure with age, so this regression result seems to be consistent with the hypothesis. As you have probably studied in your high school algebra class, the mathematical expression for a straight line is y equals a plus bx for each point on the straight line. Y is the value of its location on the vertical scale, and x is the value on the horizontal axis. A and b are parameters that define the straight line. B indicates the slope of the straight line, which means, on the straight line, if the value of x increases by 1, then the value of y increases by b. A is called the intercept or the y-intercept, which means that the diagonal line crosses with the y-axis at A. In other words, on the diagonal line, if x equals 0, then y equals A. The parameters of the straight line equation were estimated for systolic blood pressure as y, and age as x, with the NHANES data. The parameter A was estimated to be 101.9, and the parameter B, the slope, was estimated to be 0.393. The term on the left-hand side is y hat, instead of y, in order to clearly distinguish observed values of systolic blood pressure, y, and their predicted values, y hat. What does 101.9 mean? It may look like systolic blood pressure of newborn babies, because if x equals 0, then y equals 101.9. But the regression model was estimated using data for those aged 18 to 80. If persons aged under 18 follow the pattern observed for those aged 18 to 80, 101.9 may be considered as a predicted systolic blood pressure for age 0. But the age pattern of blood pressure under age 18 may be quite different from the pattern for those aged 18 to 80. So, 101.9 is considered to be a hypothetical value of systolic blood pressure at age 0, obtained by extrapolating the straight line fitted to data for age 18 to 80, to age 0. 0.393 is the slope of the straight line. According to the estimated model, if x increases by 1, then y hat increases by 0.393. So it can be considered that in this data, on average, a difference in systolic blood pressure by 0.393 millimeter of mercury, corresponds to a 1-year difference in age. On average in this sentence does not exactly mean the arithmetic mean, but means a representative value, or a typical value, and there is some mathematical reason for considering the value as representative of different values in the data. Let's play a little with these numbers. What is the value of systolic blood pressure for someone aged 45? Suppose someone is aged 45, and we predict systolic blood pressure of the person based on her or his age only. Then, according to this regression model, it is 101.9 plus 0.393 times 45, which is 119.6, or about 120. What is the difference in systolic blood pressure between two persons whose ages are 30 years apart, like age 70 and age 40? According to this equation, their typical difference is 0.393 times 30, which equals 15.3 millimeters of mercury. Or we can get the predicted values for age 70 and age 40, for example, and then compute their difference. We reviewed simple linear regression between two variables, namely systolic blood pressure and age. We saw that the relationship is fairly linear and we could use a linear model to explain the relationship.